With a giant diameter of 87,000 miles and a colorful atmosphere, Jupiter stands out as one of the most intriguing planets in the solar system. Just by casting a glance at pictures of Jupiter, one can't help but be captivated by its mesmerizing yet tumultuous environment. Why is Jupiter so darn interesting? Well, the answer lies in its perturbed environment. Unlike its serene-looking siblings, Jupiter is a maelstrom of activity. Massive storms, some even larger than our entire planet, rage across its surface, painting a picture of chaotic beauty. The high-speed winds on Jupiter make Earth's hurricanes look like a gentle breeze. We're talking about wind speeds that boggle the mind and create intricate cloud patterns that seem to dance across the gas giant's atmosphere. Nevertheless, the visible aspect of Jupiter represents only a minuscule fraction of the entire planet. What if I told you that the most captivating part of this celestial giant lies beneath its atmospheric surface? Let's uncover the secrets of Jupiter's interior, shall we? The observable quantities. Jupiter's atmosphere, like the thin skin of an apple, makes up just a tiny part of the giant planet. But what lies beneath this outer layer remains hidden from direct observation. To unravel the mysteries within, astronomers take on the challenge, employing indirect methods to piece together the composition of Jupiter's interior. The work is tough, but our patient astronomers are up to the task. Endless nights spent peering through telescopes, spanning decades or even centuries, form the backbone of humanity's quest to understand the secrets of the cosmos. Observation is the name of the game. It's about spotting something, jotting it down, pondering over the details, and then crafting an explanation that hopefully makes sense. Now put yourself in an astronomer's shoes for a moment and ask, what can I observe to unlock the secrets of Jupiter's interior? Certain observations are more valuable than others. Imagine, for example, having a grasp on Jupiter's atmospheric temperature and pressure that would be golden in our quest for understanding. Indeed, the temperature and pressure of a planet reveal critical details about its internal structure. Don't believe me? Here's why. Initial heat from formation and radioactive decay contribute to the planet's overall temperature. Pressure is indicative of core composition, with high pressure suggesting dense metallic cores. These conditions determine the states of matter in various layers, transitioning from gases to solids. Moreover, varied temperatures drive convection currents in the mantle, impacting geological processes. The likelihood of magmatic activity is influenced by temperature and pressure, visible in volcanic eruptions. Last but not least, core dynamics influenced by these factors determine a planet's ability to generate a magnetic field. It is therefore clear that studying these parameters enhances our understanding of a planet's geophysical characteristics and evolutionary history. Luckily for us, thermal maps of Jupiter can be created by combining data from multiple observations and wavelengths. These maps provide a detailed view of the temperature variations across Jupiter's atmosphere and can reveal features like hot spots, cold spots, and the overall thermal structure. Since temperature and pressure are related, they can also get a sense of how the pressure changes as you go deeper towards the planet's core. And don't forget that NASA's Galileo probe has descended into Jupiter's atmosphere, providing direct measurements of pressure. This probe used a radio occultation technique, which involved tracking the changes in radio signals as it passed through different layers of the atmosphere. Yet having details about Jupiter's temperature and pressure isn't sufficient to paint a complete picture of its interior. We need more data. Is the density consistent across the entire expanse of Jupiter, or does it undergo variations from the outer layers to the core? And if it does fluctuate, what's the pattern? A linear change with the radius, or perhaps an exponential one? Unraveling the density profile of a distant planet is no walk in the cosmic park. It demands dedicated missions tailored to the planet's specifics. In the case of Jupiter, a breakthrough came in 2018 when a study demonstrated the retrieval of density data from Juno's mission findings. Juno is a spacecraft sent there to improve our understanding of the Jovian system and the solar system as a whole. It has provided valuable insights into the density profile of Jupiter, primarily through gravitational measurements. Gravimetry involves studying the variations in a planet's gravitational field, and Juno used a technique called radio science to achieve this. The variations in Jupiter's gravitational field provide information about its interior structure, including the distribution of heavy elements and the size of its core. By comparing observed gravitational variations with computer models, scientists were able to refine their understanding of Jupiter's internal composition, density, and the transition between its gaseous outer layers and the potential solid core. Gravimetry also involves studying the perturbations on the satellite trajectory to better understand the shape of a planet. Indeed, the gravitational field of a celestial object depends on its shape and mass distribution, and the parameters that give us this information go by the name of harmonical coefficients. From these can be calculated the ellipticity, or deviation from a perfect sphere, of the planet and its departure from the theoretical shape. Crazy temperatures and model issues. Constructing an accurate model for Jupiter's internal conditions faces a fundamental challenge due to the limited availability of extensive laboratory data on hydrogen and helium properties under the extreme pressures and temperatures near the planet's center. The central temperature is estimated to be approximately 44,500 degrees Fahrenheit. This means that the internal heat source of Jupiter enables it to radiate twice as much energy as it receives from the Sun. The central pressure ranges between 50 to 100 million atmospheres, about 50 to 100 megabars, leading to the expectation that hydrogen exists in a metallic state under such immense pressures. Despite the challenges presented by these extreme conditions, the precision of the models has steadily improved. An early and significant conclusion drawn from these studies is that Jupiter cannot be entirely composed of hydrogen. Its mass would require to be much larger if that were the case. However, hydrogen must still be the predominant element, constituting at least 70% of the planet's mass, irrespective of its form, whether in a gaseous or liquid state. Helium problem. But here's the fascinating twist. According to the theories crafted by scientists, the helium content in Jupiter's upper atmosphere is anticipated to be around 28%. However, consistent measurements reveal a consistently lower figure, 24%. Where could this missing 4% be hiding? Does our model need a rethink? Well, the prevailing hypothesis among scientists is that some helium, initially dissolved in the fluid hydrogen within the planet's interior, has undergone precipitation and descended towards the planet's core. As a result, the atmosphere, the only part directly accessible to us, appears depleted of this gas. In simpler terms, assuming that 4% of the helium remains concealed from our observation, this explanation could resolve the mystery of the missing helium. Heat source. Hold on a second. We've missed a crucial detail. We've mentioned that Jupiter independently generates twice as much heat as it receives from the Sun. But how is such a phenomenon possible? What internal source is responsible for this intense heating? Well, that's an excellent question, and one that doesn't have a definitive answer yet. The currently favored explanation proposes a combination of the gradual release of primordial heat left from the planet's formation and the liberation of thermal energy resulting from the precipitation of helium droplets in the planet's deep interior, similar to processes observed on Saturn. The lower abundance of helium in Jupiter supports this latter hypothesis, adding another layer to the ongoing quest to unravel the mysteries of Jupiter's internal heat sources. Hey, before moving on, be sure to like or dislike the video so that we can improve it for you, the viewer. Plus, don't forget to subscribe to our channel by making sure to hit the notification bell so you don't miss any of our daily videos. Putting the pieces together. Putting together all the knowledge we have, here's what the structure of Jupiter looks like. First, there's the atmosphere, a swirling mixtape of gases, hydrogen, helium, a bit of methane, water, and some ammonia ice particles. Here the temperature swings from freezing to super hot, and the pressure is kind of like the squeeze you feel underwater, but up to 1,000 times. Then, there is the outer interior. You can find it just a bit below the atmosphere. This is a layer where liquid hydrogen and helium are throwing their own shindig. There's a sprinkle of methane, water, and ammonia, and the pressure is cranked up to something like 200,000 atmospheres. There's literally no way anyone on Earth could survive on this planet. It's getting serious, and the temperature's heating up. Deeper still, things get wild. Picture a liquid metallic hydrogen disco ball with a splash of helium, methane, water, and ammonia. The pressure is sky high from 200,000 to a whopping 45 million atmospheres. And the heat? We're talking a blazing 14,432 to 28,832 degrees Fahrenheit. It's basically an immense cauldron. Finally, our journey ends at Jupiter's core, the treasure chest. Is it solid or liquid? Does it even exist? We don't really know. Before we move on to the core debate, be sure to stay tuned afterwards if you haven't seen our earlier release on what a journey to the solar system planet's core would look like. The core debate. In the debate about Jupiter's origin, most theories point to a solid core, a heavyweight champion that emerged during the solar system's early days. However, an opposing theory challenges this, suggesting that Jupiter might be all gas with no core whatsoever. Proponents of this first theory argue that Jupiter's core grew so massive that it wielded through gravitational pull to snag even the lightest elements, hydrogen and helium. As more gas piled up, the giant gas ball we recognize as Jupiter took shape. On the flip side, supporters of the secondary theory believe Jupiter emerged from a vast cloud of gas and dust surrounding the Sun post-birth. This cosmic cloud cooled and denser regions formed as gas and dust particles clumped together. From one of these dense patches, a gravitational pull gathered more material, birthing Jupiter. Juno, with its high-tech instruments, plans to unravel this mystery by measuring Jupiter's gravitational and magnetic fields with unprecedented precision. If a core exists, the field's characteristics will offer clues about its size, providing a cosmic compass to navigate the competing theories. The outcome might strengthen the core-centric theory hint that Jupiter once had a core now eroded away, or possibly throw a curveball that demands brand new cosmic theories. The universe, it seems, loves to keep us on our toes. Whether Jupiter boasts a core or not, there's no denying that this planet holds an awesome, inspiring allure that transcends our wildest imagination. Whoever crafted the universe, whether through a self-creation process or the hands of a divine force, undeniably fashioned a masterpiece. Beauty echoes throughout the cosmos, and we're fortunate to possess brains capable of comprehending the intricate world unfolding around us each day. Let kindness guide you, and never forget to keep that insane curiosity alive. What a journey to the core of solar system planets would look like. In Jules Verne's famous novel, Journey to the Center of the Earth, the protagonists of that incredible adventure made it to the heart of our planet by traversing forests grown in great hollows, rivers of lava, and lakes of water, and escaping the pitfalls of a real underworld populated by prehistoric creatures. Just a good story, of course. How could Jules Verne have known, in fact, in the 19th century, what the interior of the Earth looked like? In our time, fortunately, we know a lot more. No descents down endless caverns, then no chasms in the center of the Earth. No inner worlds, subterranean seas, dinosaurs, or cavemen. The Earth is a compact sphere filled with materials at very high temperatures. Yeah, but are we really sure? And how do we know? After all, the maximum depth reached by a borehole is 12 kilometers, or only 500th part of the Earth's radius, a mere nothing. Yet that's just the way it is. By now we can say that we have a very good knowledge of what lies beneath the Earth's crust, and a fair knowledge of the internal composition of the other planets in the solar system. Strange, isn't it? And how would we have done that? With what magic wand would we have succeeded? What do you say? Let's try together to figure it out. Apart from boreholes, which are totally insufficient for the purpose, astronomers have many other tools to probe the interior of planets. By carefully observing the rotation of a planet, for example, it's possible to detect the presence of very small oscillations of its axis of rotation, and the amount and magnitude of these oscillations depend on a parameter called the moment of inertia, which can give useful insights into how mass is distributed within the planet. The cores of Earth-type planets, to say, are much denser than their surface crust, and Jovian planets have an even greater concentration of mass in their cores. Small twists in the rotation of an Earth-like planet can therefore be used to determine whether the core is solid or liquid. For example, the variations in Mercury's rotational velocity are too great to be caused by a completely solid core, so its core, or parts of it, must be liquid. This is easily guessed. For the same applied force, a sphere filled completely with water will rotate faster than a similar sphere filled only halfway with water, where the liquid slips over the inner surface and, with its friction, resist rotation. The mass distribution of a planet can also be deduced by observing the movements of satellites, natural moons, or spacecraft in the planet's gravitational field. Any gravitational anomaly of the planet will indeed have well-detectable consequences on their orbital motion. Just to say, the GRACE mission, an acronym for Gravity Recovery and Climate Experiment, has orbited the Earth long enough, over 15 years, to even map decreases in the amount of Earth's ice near the poles and decreases in the amount of water and groundwater by pumping water for agriculture. But it's not just Earth, on the other planets too. From Mercury with the MESSENGER probe to Saturn with Cassini, the method has worked great. Measurements and changes in velocities from NASA space probes orbiting Mars have been used to create maps of its gravitational field. And the Juno probe has done the same thing with Jupiter, arriving at interesting results about the nature of its core. Perhaps the most widely used in such research, however, is that of seismic wave analysis. Seismologists have already realized for at least a century, in fact, that seismographs, the graphs that record the course of seismic waves passing through the Earth in each direction, can be read as if they were X-rays of the planet. In other words, earthquakes travel through the planet as waves, and these waves travel at different speeds through different materials, and can also be reflected when they encounter a discontinuity in the layers. Seismic waves carry with them a range of information about the nature of the materials they have passed through, in the form of variations in their propagation velocity and the direction of their trajectories. In fact, their speed depends on the medium in which they propagate. Thanks to information gained from the study of seismic data, we now know that the Earth consists of concentric envelopes, which are made up of materials that differ in density and in the physical state in which they occur, solid or fluid. Such a technique has obviously been tested on our planet, and then on the Moon and Mars. So this is how we can make pretty good guesses about what the interiors of Mercury, Venus, Earth, Moon, and Mars look like. We can also use these methods to infer the internal structure of some of the best studied moons in the outer solar system: Io, Europa, Ganymede, and Callisto. For gas giants, it's a bit more difficult because they do not tend to have distinct layers like rocky planets. Also, they are so huge that the pressures and temperatures in their inner depths are much greater than we can simulate in the lab. So we have to rely on theoretical predictions rather than actual data to understand how the materials involved behave. Anyway, here is in brief what we know today about the physical and chemical structure of the Moon and the planets of the solar system. Mercury. Mercury's density of 5.4 grams per cubic centimeter is very close to Earth's. This suggests that despite its similarities to the Moon, the planet's internal structure is more like that of Earth. While Earth's high density is the result of strong gravitational compression, Mercury is much smaller, and the inner regions are therefore less compressed than those on Earth. Therefore, such a high density assumes that the core must be relatively larger and iron-rich. Based on data from the Mariner 10 probe, it is assumed that Mercury's surface crust should be about 200 kilometers thick, and that underneath should extend for 600 kilometers a thick silicate mantle surrounding a large core 2,000 kilometers in radius. Or perhaps even a double core, with a solid central shell and an outer semi-fluid one. Relative to its diameter, Mercury has the largest core in the solar system, with the highest iron content on the record. Venus. Although there is little direct information about the Venusian internal structure due to the lack of seismic data, the similarities in size and density between Venus and Earth suggest that the two planets may have a similar internal structure: a core, mantle, and crust. The Venusian core, like Earth's, is believed to be at least partially liquid, since the two planets have undergone a similar cooling process. The main difference between the two planets is the absence on Venus of plate tectonics, which is probably due to the different composition of the Venusian lithosphere and mantle compared to Earth's. The absence of water leads to a higher viscosity and thus a higher degree of coupling between the crust and mantle. The Moon. During the various Apollo missions to the Moon, several instruments were left on the surface of our natural satellite, including seismographs, gravimeters, and magnetometers. These instruments transmitted for several years data that proved to be very useful in letting us know, at least in general terms, about its internal structure. From a seismological point of view, much weaker earthquakes occur on the Moon than on Earth and are thought to be dependent on its position relative to Earth. In fact, lunar earthquakes occur twice a month. That is when the Moon is closer and farther away than our planet. The Moon's internal structure is similar to Earth. It consists of a core, the innermost layer, a mantle, the middle layer, and a crust, which represents the surface layer. The crust is thinner on the side facing Earth, where it averages about 60 kilometers thick, than on the opposite side, where it is about 100 kilometers thick. In it are the seas, having a thickness of 5 to 20 kilometers. The crust, together with the upper part of the mantle, forms the rigid lunar lithosphere, about 1,000 kilometers thick. The mantle consists of materials of higher density than the crust. Below the mantle is the plastic asthenosphere, which probably has a chemical composition similar to that of the mantle, but where the rocks are in a partially molten state. Thickness is about 350 kilometers. The core, with an estimated diameter of about 600 kilometers, is the portion of the Moon about which knowledge is most uncertain. It is assumed to consist at least partly of iron and nickel. Mars. The crust, mantle, and core of Mars formed within about 15 million years of the birth of the solar system and remained active for the first billion. The crust has an average thickness of 50 kilometers with a peak of 125 kilometers. Compared with Earth's crust, which has a thickness of about 40 kilometers, one could say that the Martian crust is 3 times thicker, considering it is twice the size of our planet. The mantle, which is denser than Earth's, is composed mainly of silicates and, although it is inactive, is the source of all tectonic and volcanic phenomena on the planet. The core is composed mainly of iron and nickel, with around 16% sulfur, and extends for a radius of about 1,800 kilometers. Most likely the core is solid, but in a viscous state. As a result, Mars has no appreciable magnetic field. This results in the lack of protection of the planet's soil from the activity of high-energy cosmic particles. Saturn. Saturn's internal structure is not much different from that of Jupiter, except for a more complete differentiation of the innermost layers. The center of the planet, where temperatures probably reach 15,000 degrees, there would be a rocky core of silicates and metals surrounded by a shell of icy materials such as water and ammonia. Surrounding this solid core, which is expected to have a radius of nearly 15,000 kilometers, would extend a mantle of liquid hydrogen in which 2 layers would stand out. As on Jupiter, an inner layer of metallic hydrogen that is ionized hydrogen and an outer layer of molecular hydrogen. Above the ocean of liquid hydrogen extends the atmosphere. However, the transition from the liquid to the gas phase occurs gradually without a clear boundary. The results show how the core may not be entirely rocky, but more fuzzy, a kind of soup of ice, rock, and metal fluids that stretches across 60% of the planet's diameter, thus larger than classical theories. A surprising result, however, goes well with what has been inferred from the Juno probe's data on Jupiter, whose core seems similarly diluted. It is hard to imagine, but Saturn is the only planet in our solar system whose average density, 0.7 grams per cubic centimeter, is less than that of water. The giant gaseous planet could float in an ocean that was capable of containing it. Uranus. The structure of Uranus is similar to that of the inner part of Jupiter and Saturn. However, due to the lower mass, which is insufficient to generate the enormous pressures on these 2 planets, it lacks the liquid metallic hydrogen envelope. The material should also be more evenly distributed without the presence of a true rocky core. Uranus's core, however, is relatively small and not very massive. It also differs from that of the other giant planets in that it dissipates little heat. In astronomical terms, it has a low heat flux. It's not clear exactly why Uranus radiates little energy outward. One hypothesis put forward to explain this difference from other gas giants is that when Uranus was stuck in the body impact that caused its peculiar axial tilt, most of the original internal heat was expelled, significantly reducing the core temperature. Outside the core is a liquid mantle composed mainly of ice, methane, and ammonia, 7,500 kilometers thick, then a gaseous atmosphere, 7,600 kilometers thick, consisting mainly of hydrogen and helium, with a small portion of methane and traces of other gases, water, and ammonia. Neptune. Neptune has a similar composition to Uranus and consists mainly of ice and rock, with about 15% hydrogen and a small part of helium. Its structure is similar to that of the inner part of Jupiter and Saturn. However, due to the lower mass, which is insufficient to generate the enormous pressures on these two planets, it lacks the liquid metallic hydrogen envelope, and the material should be more evenly distributed, with no clear distinction between the different layers. In the central part, however, there is a small iron core of rock and ice. And so, dear friends, it seems that we must also say goodbye to the imaginative possibility described by Jules Verne, that of being able to explore the interiors of the planets simply by following the immense cavities capable of leading us to their centers. The planets, as we have seen in this video, are huge spheres of very compact matter, and moreover, very hot. No hope of finding monsters, other worlds, and pretty girls in skimpy costumes there.